Okay, let's start with the rabbit puzzle from last time. So a ship leaves a pair of baby rabbits on an island with a lot of food so that they can survive and live a good life. And after they reach 2 months of age, so let's say in 2 months, they produce another pair of baby rabbits. And that first pair keeps producing a pair every month after. So again, things are not biologically realistic here, but oversimplifying, let's say the first pair is producing a pair of rabbits every month after starting at 2 months of age, and the baby rabbits, when they reach 2 months of age, they start producing baby rabbits. So the pair born when the original pair is at 2 months, when they reach 2 months, they produce baby rabbits. So the question is, how many pairs of rabbits will be on the island in n months? There is lots of food, there are no predators. All the rabbits do is eat and reproduce. So let's count. So let's see. Month 0, there is nothing, no rabbits. At month 1, there is a pair of rabbits brought to the island. In month 2, they become adults, and at month 3, they produce a pair of baby rabbits because by month 3 they're 2 months old if they were born in month 1. Month 4, the pair born at month 3 becomes adults, and the original pair produces another pair of baby rabbits. It happens at month 5. Well, now we have 3 pairs of adults and 2 pairs of babies because the original pair gave us yet another pair. The firstborns that became adults last month gave a pair, and the pair of rabbits that was babies last time became adults. So the sequence is about 0, 1, 1 again, then we have 2, then we have 3, then we have 5, and then we keep going. So here is the sequence, and you probably noticed that the number of rabbits at every month can be more or less described by the number of rabbits the month before that plus the number of rabbits and 2 months before that. And why is that? Well, if you look at rabbits as babies and adults, all the rabbits that were already born 2 months ago would give us a pair of baby rabbits. So the number of baby rabbits is the number of pairs alive 2 months ago. And in addition, everybody alive a month ago became either already an adult or became an adult. So the number of adult pairs is the same as the number of rabbits alive 1 month ago. And the total number of babies plus adults is the number of rabbits alive a month ago plus the number of rabbits alive 2 months ago. And this is a description of how the sequence of rabbits work, how those rabbits reproduce. This sequence and that rabbit puzzle goes back to Fibonacci, a famous mathematician, and it's usually called Fibonacci sequence or sometimes Fibonacci numbers. 0, 1, 1, 2, 3, 5, the next one will be 8, 8 plus 5, 12, and then it keeps going. So I use the word sequence without defining it, but generally we will mean by sequence just some list of things, of elements from some set. We could talk about it as a function that takes a number, so say 0th element, first element, second element, and tells us what the element is. For example, in the Fibonacci sequence, the element number 3 is equal to 2. And by the way, here I'm using A0, A1, A2. It completely doesn't matter just some kind of a letter or something is good. For example, for Fibonacci, we use capital F, F0, F1, and so on. Often, because it's a sequence S0, S1, and so on, I used the very first, the zeroth element of the sequence is called the initial term. And for every term of the sequence, say A sub I or S sub I, will be just the value of that function enumerating elements of the set S at number I. So two very common examples of sequences, more common even than Fibonacci numbers, are arithmetic progression and geometric progression. Arithmetic progression is a sequence that you build by taking a number and keep adding another number to it. For example, if you take number 2 and keep adding 3 to it, well, at the beginning you just have 2. Your second number is 2 plus 3 is 5. Your third number is 5 plus 3 is 8. By the way, nothing in common with Fibonacci sequence. The next number is 8 plus 3, 11. The one after is 11 plus 3, 14, and so on and so forth. So different A and different D will give you a different sequence, but because this is a sequence of the form a number plus one copy of another plus 2 plus 3 plus 4 of the other one, all of them are called arithmetic progressions. Geometric progression is very similar, but instead of adding a number to an initial one, you multiply the initial by something else. So initial term in both cases is some number A, let's say 2. And for geometric progression, the term S1 will be 2 times, in this case, that number is 3, so 2 times 3 is 6. The next one will be 2 times 3, and again times 3 will be 18, and so on and so forth. So you could tell that when I was describing those sequences, a lot of time the way I would say how they work is by saying how you get the next number out of the previous ones. I was saying the number of rabbits at time n is the sum of the number of rabbits at time n minus 1 and number of rabbits at time n minus 2. So I kind of assumed that you already got to n by getting through n minus 1 and n minus 2. So by the time you're computing f sub n, you know f sub n minus 1 and f sub n minus 2, and you could just add them up. So this kind of description, when you express the next element of a sequence in terms of the previous one, is called a recurrence. And a lot of time it's used not just for sequences, but very commonly for functions, for running times of programs, and so on and so forth. And now we could define our sequences by using a recursive definition, which will consist of a recurrence together with the value of initial term. Well, sometimes you need several initial terms. For example, for Fibonacci numbers, you need f of 0 and f of 1, and then you could start computing the next one using this formula. So here are some examples of recursive definitions. So for Fibonacci sequence, the basis is f of 0 is a 0, f of 1 is a 1, and then the recurrence you've seen already several times, number of adults plus number of babies, f of n minus 1 plus f n minus 2 will give you f of n. Arithmetic progression, again, kind of said it already, that the next number is the previous number plus that number d that you keep adding to the original one. Geometric progression, similar. Instead of adding, you multiply, but otherwise it is the same. And it doesn't have to be numbers. It can be sequence of whatever you want. For example, I could talk about sequence of power sets by saying I'll start with an empty set, then I'll take a power set of it, then I'll take a power set of the power set of it, and I keep going. And we've seen it already when we talked about cardinalities of set by saying a power set of a set is always bigger. So here I'm building a sequence of bigger and bigger and bigger sets, even though I started with nothing. I started with an empty set. So for the next time, think about this puzzle. You might have seen it already when you were a lot younger, but the puzzle called the Tower of Hanoi works as follows. You have some number of disks, in this case it's 8, and you have 3 pegs. And at any move, you could do the following. You could take a disk from one peg and put it on another one, with the condition that you can never put a big one on top of the small one. You could always put anything on an empty peg, but you cannot put, for example, a red disk in the first picture on the second peg on top of the green one, because the red one is bigger than the red one in the first picture is bigger than the green one on the first peg. So here is the question: how many steps do you need to move the tower of, let's say, 8 disks from first peg to the second one, if your every move obeys this rule that you never put something on top of something smaller? And just to generalize, how would you do it not for 8 disks, but for n disks, for an arbitrary n, as we did for the rabbits for n months? So think about it for next time.